Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The name Sergei Korolev, often veiled in the shadows of Cold War secrecy, represents a pivotal figure in the annals of space exploration. His contributions, initially obscured by the Iron Curtain, fundamentally reshaped our understanding of technology, geopolitics, and the very aspirations of humanity. The launch of Sputnik 1 on October 4, 1957, a feat spearheaded by Korolev and his team, served as a stark demonstration of Soviet technological prowess, instantly altering the global landscape. The satellite's simple, yet elegant, design belied the complex engineering challenges that Korolev and his team masterfully overcame. The core objective, to place a man-made object into orbit, presented a myriad of hurdles. The central challenge resided in miniaturization. The radio transmitter, the heart of Sputnik's communication system, had to be compact and robust enough to withstand the rigors of launch and the vacuum of space. The team, driven by Korolev's relentless pursuit of innovation, successfully developed a transmitter that, while primitive by today's standards, sent a clear signal back to Earth, a beacon of Soviet achievement. This signal, a simple beep beep beep, became a symbol of a new era. The frequency, meticulously chosen, was 20.005 and 40.002 MHz, allowing amateur radio operators across the globe to detect the satellite's presence and confirm its orbital trajectory. Powering this transmitter presented a significant dilemma. The initial design contemplated solar panels, a technology still in its infancy. However, the timeframe and the technological limitations of the era favored a more pragmatic solution: chemical batteries. These batteries, designed to last for a few weeks, provided the necessary electrical energy. The decision reflected Korolev's characteristic pragmatism, a focus on achieving the immediate goal, even if it meant sacrificing some long-term advantages. Thermal management, a critical consideration for any spacecraft, posed another significant challenge. The extreme temperature variations encountered in the upper atmosphere, ranging from intense solar radiation to the deep cold of space, could cripple the satellite's internal components. Korolev's engineers devised a system of thermal control, relying on the satellite's spherical shape and carefully selected materials to radiate heat effectively. The polished surface of the sphere acted as a reflector, minimizing heat absorption from the sun. The design, though seemingly simple, demonstrated a deep understanding of thermodynamics and the practical application of these principles. Sputnik 1, a sphere measuring 58 centimeters in diameter and weighing approximately 83 kilograms, was a testament to this ingenuity. The satellite's orbital parameters, meticulously calculated, placed it in an elliptical orbit, circling the Earth every 96.2 minutes. The apogee, the farthest point from Earth, reached 947 kilometers, while the perigee, the closest point, was 215 kilometers. This orbit enabled the satellite to gather valuable data about the Earth's upper atmosphere and the effects of space on its systems. The radio signals transmitted from Sputnik 1 also provided crucial information about the density of the ionosphere, a layer of charged particles that surrounds the Earth. The launch of Sputnik 1 triggered an immediate and profound global reaction. For the Soviet Union, it represented a monumental triumph of indication of its scientific and technological investment. The success of Sputnik 1 was a potent propaganda tool, showcasing the Soviet Union's capacity for scientific advancement and its ability to compete with and surpass the United States in the space race. The event had a galvanizing effect on Soviet society, fostering national pride and a sense of collective achievement. The United States, however, experienced a different reaction. The launch of Sputnik 1 caused a wave of shock and concern. The American public, accustomed to their nation's perceived technological superiority, found themselves confronted with the reality of Soviet achievement. The event triggered a national crisis, prompting a reassessment of American scientific and technological capabilities. The initial response was marked by a sense of vulnerability, a feeling that the United States had fallen behind in a crucial area of technological competition. The government responded with a surge in funding for scientific research and education, aiming to close the perceived space gap. The scientific community, while initially surprised, quickly recognized the significance of Sputnik 1. The satellite's successful launch confirmed the feasibility of space travel, opening up a new frontier for scientific exploration. The data transmitted by Sputnik 1, though limited, provided valuable insights into the Earth's upper atmosphere and the space environment. The event stimulated a surge of interest in space science, leading to a rapid expansion of research and development in the field. The impact of Sputnik 1 extended far beyond the realm of science and technology. The event had a transformative effect on the United States education system, particularly in mathematics and science. The launch of Sputnik 1 served as a catalyst for educational reform, prompting a renewed emphasis on STEM subjects: science, technology, engineering, and mathematics. The government initiated programs to improve the quality of science and mathematics education, including funding for teacher training, curriculum development, and the construction of new laboratories and research facilities. The National Defense Education Act, passed in 1958, provided significant financial support for education in these critical fields. This act offered loans to students pursuing higher education in science and engineering and provided grants to schools and universities to improve their science and math programs. This investment had a long-lasting impact, fostering a new generation of scientists, engineers, and mathematicians. The influence of Sputnik 1 extended to the very structure of scientific research and development. The event motivated the establishment of the National Aeronautics and Space Administration, or NASA, in 1958. NASA, a civilian agency, was charged with coordinating the United States space program. NASA's formation consolidated the nation's space efforts, bringing together various research and development programs under a single umbrella. This streamlined approach proved to be essential for the United States' subsequent successes in space exploration. The legacy of Sputnik 1 is multifaceted. The launch of the satellite represents a pivotal moment in human history, a testament to the power of human ingenuity and the boundless potential of scientific exploration. The event spurred a global competition for technological supremacy, leading to unprecedented advancements in science and technology. The impact of Sputnik 1 on education, scientific research, and international relations continues to resonate today. The launch of Sputnik 1, orchestrated by Sergei Korolev and his team, was a landmark achievement forever changing the course of human history. The genesis of Sergei Korolev's engineering philosophy can be traced to his early experiences, particularly his involvement in the nascent rocketry programs of the Soviet Union during the 1930s. The intellectual and practical problems he confronted during this period profoundly shaped his approach to design, management, and innovation. His work at GERD, the Group for the Study of Reactive Motion, provided a crucial proving ground. GERD, established in 1931, represented one of the earliest organized efforts to explore the possibilities of rocket technology in the Soviet Union. Korolev, a young, ambitious engineer, quickly became a leading figure in this small but dedicated community. At GERD, Korolev and his colleagues tackled fundamental challenges. The primary focus was on developing liquid propellant rockets, a technology still in its infancy. The team grappled with the intricacies of propellant management, ensuring the reliable delivery of fuel and oxidizer to the combustion chamber. They experimented with various propellant combinations, seeking to optimize performance and stability. Combustion stability itself presented a significant hurdle. The violent and unpredictable nature of the combustion process could lead to catastrophic failures. The engineers had to devise methods to control and stabilize the burning of the propellants, preventing destructive oscillations and ensuring efficient energy release. Furthermore, the selection of materials capable of withstanding the extreme temperatures and pressures within the rocket engine was a constant concern. Metals had to be chosen with properties that could endure the harsh conditions of flight. The Vertex rocket, launched in 1933, marked a significant milestone. It was the first Soviet rocket propelled by a liquid propellant engine to achieve flight. This achievement, though modest by later standards, demonstrated the feasibility of liquid propellant rocketry and provided invaluable practical knowledge. The Verdex's engine, designed by Mikhail Tikhonravov, utilized liquid oxygen and gasoline as propellants. The rocket's design incorporated several innovative features, including a stabilizing fin system and a parachute recovery system. The Vertex provided a tangible demonstration of the theoretical principles of rocket propulsion. The research and development at GERD were strongly influenced by the theoretical work of Konstantin Tsiolkovsky, often considered the father of Russian cosmonautics. Tsiolkovsky, working decades earlier, had laid out the fundamental principles of rocket propulsion and space travel. Korolev, like many other early rocket pioneers, was deeply familiar with Tsiolkovsky's writings. Tsiolkovsky's equations, particularly the rocket equation, which relates the change in velocity of a rocket to its exhaust velocity and the mass ratio of the rocket, were fundamental to the design process. The equation, often written as delta V equals exhaust velocity times the natural logarithm of the initial mass divided by the final mass, provided a mathematical framework for understanding the factors that determined a rocket's performance. Tsiolkovsky also envisioned multi-stage rockets, a concept that would later become essential for achieving orbital velocity. In addition, Tsiolkovsky's ideas about the use of liquid propellants and his understanding of the vacuum of space were all essential to Korolev's work. Tsiolkovsky's work provided the theoretical foundation upon which Korolev built his practical engineering expertise. However, Korolev's career faced a devastating setback. In 1938, he was arrested during the Stalinist purges. He was accused of counter-revolutionary activities and sentenced to imprisonment in a labor camp, the Kaula region. The experience was brutal, and the interruption to his work was profound. The loss of freedom, the harsh conditions, and the disruption to his research undoubtedly had a significant impact on his life and career. After his release, Korolev's focus shifted. He was assigned to work in a special design bureau, the Asterisk Tupol of Sharisher Asterisk, where he collaborated on aircraft design. This experience, while not directly related to rocketry, provided him with valuable knowledge of aerodynamics, materials science, and engineering management. The experience was transformative. The aftermath of World War IV presented both opportunities and challenges. The Soviet Union seized a significant amount of German rocket technology, including captured VH-2 rockets and documentation. This provided invaluable insights into advanced rocket design. The VH-2, developed by Werner von Braun and his team, represented a major technological leap forward. It was the first large-scale, liquid propellant-guided missile. The Soviet Union recognized the strategic value of this technology and initiated a crash program to replicate and improve upon the VH-2. The reverse engineering of the V-2 presented numerous difficulties. The Soviet engineers, including Korolev, had to decipher the complex design, understand the manufacturing processes, and overcome the limitations of Soviet industrial capacity. The V-2 utilized advanced technologies, including a sophisticated guidance system, a complex engine design, and specialized materials. The Soviet team had to develop their own versions of these technologies, often starting from scratch. The experience of working on the V-2 had a profound influence on Korolev's approach to rocket design. The V-2's engine, the A-4 engine, was a complex and powerful design. The Soviet engineers had to master the intricacies of this engine, including its combustion chamber, propellant injectors, and cooling systems. The V-2's guidance system, which used gyroscopes and accelerometers to control the rocket's trajectory, was also a significant challenge. The Soviet engineers had to develop their own inertial guidance systems, which were essential for achieving accurate targeting. Korolev and his team learned from the German experience. The V-2's design, while sophisticated, also had its weaknesses. The rocket was prone to failures, and its guidance system was relatively inaccurate. The Soviet engineers, drawing on their experience with the V-2, sought to overcome these limitations. They focused on improving the reliability of their rockets, developing more robust guidance systems, and optimizing the performance of their engines. The challenge of developing reliable propulsion systems was paramount. The performance of a rocket is directly dependent on the efficiency and reliability of its engine. Korolev recognized this and devoted considerable resources to engine development. He collaborated closely with Valentin Gleshko, the chief rocket engine designer, a partnership that would prove crucial to the success of the Soviet space program. Gleshko's work on rocket engines, including the RD-107 and RD-108 engines, was a critical element of the R-7 rocket, which would later launch Sputnik 1. To advance their work, Korolev's team employed various tools and techniques. The development of wind tunnels was essential for studying the aerodynamic properties of rocket designs. Wind tunnels allowed engineers to simulate the conditions of flight and to test different designs, identifying and correcting problems before the rocket was built. Experimental testing rigs were also crucial. These rigs allowed engineers to test components and systems under realistic conditions. Static firing tests in which the engine was fired while held in place, were used to assess the engine's performance and to identify potential problems. The team also developed sophisticated instrumentation to measure various parameters, such as thrust, pressure, and temperature during these tests. Through these early experiences, Korolev honed his engineering skills, developed a deep understanding of the challenges of rocket design, and cultivated a pragmatic and innovative approach to problem solving. He learned the importance of collaboration, the value of rigorous testing, and the need to embrace new technologies. These formative experiences laid the foundation for his later achievements, including the launch of Sputnik 1 and the Soviet Union's pioneering role in the space age. The progression from early rocket experiments to the dawn of the space age was marked by the development of a weapon that would reshape global power dynamics, the R-7 Semi-Arc Intercontinental Ballistic Missile, or ICBM. This formidable machine, initially conceived for delivering nuclear warheads, would unexpectedly become the vehicle that propelled humanity into orbit. The R-7, more than any other single technological feat, embodies the ingenuity and the unique set of circumstances that defined Korolev's leadership. The R-7's design addressed a fundamental challenge of the creation of a rocket capable of traveling vast distances, reaching across continents to deliver its payload. The Soviet Union, acutely aware of the United States' nuclear capabilities, recognized the strategic necessity of developing its own long-range delivery system. This imperative provided the impetus and the resources for the ambitious project. The initial specifications demanded a rocket able to carry a heavy warhead over thousands of kilometers. This required a radical departure from the comparatively modest V-2, the German rocket that had served as a crucial point of reference and a source of captured technology for both the Soviets and the Americans after the Second World War. The R-7's design was a marvel of engineering, a testament to Korolev's ability to synthesize diverse technologies and to push the boundaries of what was then possible. Its most distinctive feature was its cluster arrangement of engines. The first stage comprised 4 boosters, each powered by a single RD-17 engine. The central core, the second stage, was propelled by an RD-118 engine. Both engine types, the heart of the R-7's power, were designed by Valentin Glushko, whose contributions were pivotal to the rocket's success. Glushko, an extraordinarily talented engineer, possessed a deep understanding of rocket engine technology. He had a strong personality, which sometimes led to conflicts with Korolev, but their collaboration proved to be essential. Glushko's engines employed a closed-cycle design, a sophisticated approach that improved efficiency and performance. They utilized liquid oxygen and kerosene as propellants, a combination that offered a good balance of performance and stability. The RD-117 and RD-118 engines represented a significant advance over the V-2's engine, which had a simpler design. Glushko's engines generated immense thrust, allowing the R-7 to lift its heavy payload. The engine's design, however, presented considerable challenges. The engines had to be incredibly reliable, as any failure could result in the destruction of the rocket. The engines also had to be precisely synchronized to ensure that the rocket maintained its course. The RD-17 and RD-18 engines, with their intricate systems and demanding performance requirements, required meticulous engineering, rigorous testing, and constant refinement. The success of the R-7 was, in large part, a consequence of Glushko's persistent dedication to engine development. The R-7's guidance system was another critical area of innovation. The rocket employed an inertial guidance system, a sophisticated technology that used accelerometers and gyroscopes to determine the rocket's position and velocity. The system, developed by a team of engineers and scientists, allowed the R-7 to navigate to its target with remarkable accuracy. This was a significant improvement over the VA-2's simpler guidance system, which had been less precise. The inertial guidance system was essential for the R-7's effectiveness as a weapon, ensuring that it could deliver its warhead to the intended location with a high degree of certainty. The construction of the R-7 demanded exceptional structural integrity. The rocket had to withstand tremendous forces during launch, including the immense thrust of the engines and the aerodynamic stresses of traveling at supersonic speeds through the atmosphere. The rocket's structure was primarily constructed from aluminum alloys, carefully designed to balance strength and weight. The engineers had to consider a wide range of factors, including the distribution of stresses, the effects of temperature changes, and the vibrations generated by the engines. The design also had to accommodate the liquid propellants, which required specialized tanks and plumbing. The R-7's robust design enabled it to withstand the rigors of launch and to deliver its payload reliably. The adaptation of the R-7 for spaceflight involved several modifications. The most significant change was the removal of the warhead and its replacement with a payload, such as the Sputnik satellite. This, however, was a relatively straightforward modification. The rocket's basic design, with its powerful engines and robust structure, was well suited for launching satellites into orbit. The primary challenge was ensuring that the satellite could survive the launch environment and function properly in space. The R-7's journey through the atmosphere presented additional difficulties. The rocket had to withstand extreme temperatures generated by aerodynamic heating during its ascent. The solution was to use a heat shield, a specialized material designed to absorb and dissipate heat. The heat shield, a crucial component of the rocket's design, protected the satellite from the intense heat of re-entry. The R-7's aerodynamic stability was also a concern. The rocket had to maintain its course through the atmosphere, which required careful attention to its shape and control systems. The engineers used fins and other aerodynamic surfaces to stabilize the rocket and to steer it in the desired direction. The legacy of the R-7 extends far beyond its initial role as a weapon. The rocket's success demonstrated the Soviet Union's technological prowess and initiated the space age. The R-7's design served as the foundation for a series of subsequent launch vehicles, including the Vostok rocket, which carried Yuri Gagarin, the first human in space. The R-7's impact on space exploration is undeniable. Its development spurred innovation in rocket engine technology, guidance systems, and structural engineering. The R-7's influence is still felt today, as its basic design principles continue to inform the development of modern launch vehicles. The rocket's success was a testament to the vision of Korolev, the engineering expertise of Glushko, and the collective effort of the many individuals who contributed to the project. It was a technological achievement that transformed the world. The remarkable trajectory of the R-7, from a strategic deterrent to a gateway to the cosmos, underscored the crucial role of organizational prowess, a domain where Korolev truly excelled. He understood that realizing ambitious goals in rocketry required more than ingenious designs. It demanded the orchestration of diverse talents, the management of complex projects, and the navigation of a labyrinthine bureaucratic landscape. He became the central figure in the Soviet space program, wielding influence that extended far beyond the confines of the Design Bureau. At the heart of this organizational structure was OKB-1, the Experimental Design Bureau No. 1. This was Korolev's primary domain. It was not merely a design office, it was a nexus of scientific and engineering expertise, a collaborative environment where ideas were exchanged and innovations took shape. Within OKB-1, teams of specialists worked on various aspects of the rocket and spacecraft development, from propulsion systems to guidance and control mechanisms. Korolev fostered a culture of open communication, encouraging collaboration across different disciplines. He had the remarkable ability to grasp the intricacies of each technical challenge while simultaneously maintaining a strategic overview of the entire program. The Soviet system, however, presented unique hurdles. Secrecy, a ubiquitous feature of the Cold War era, cast a long shadow over the space program. Information was tightly controlled, hindering open scientific exchange and collaboration with external entities. Resources were allocated according to political priorities, which could sometimes lead to inefficiencies and delays. Korolev, however, proved adept at maneuvering within this environment. He possessed a keen understanding of the political landscape and cultivated strong relationships with key figures in the government and the military. He used his influence to secure funding, resources, and the necessary approvals for his projects. His ability to navigate these complexities was critical to the program's success. The Vostok program, the initiative that would ultimately place the first human in space, exemplified Korolev's organizational and engineering acumen. The Vostok spacecraft, a marvel of engineering, was designed to carry a single cosmonaut into orbit. Its design was a direct consequence of the limitations imposed by the R-7 rocket. The Vostok capsule, a sphere approximately 2.5 meters in diameter, was intentionally kept small to fit within the confines of the rocket's payload capacity. The design prioritized simplicity and reliability, recognizing the inherent challenges and risks associated with manned spaceflight. Life support systems were crucial for the cosmonauts' survival. The Vostok incorporated a closed-loop system to provide oxygen, regulate temperature, and remove carbon dioxide. It included a system that provided food and water in a compact and easily accessible form. The ejection seat, a distinctive feature of the Vostok design, was a critical safety measure. Upon re-entry, the cosmonaut would eject from the capsule at a specific altitude and descend to Earth via parachute. This design choice, necessitated by the capsule's inability to land safely with the cosmonaut inside, was a subject of some controversy, although it was, at the time, the only viable option. The heat shield, another essential component, protected the spacecraft and its occupant during the fiery re-entry into the Earth's atmosphere. The heat shield was designed to absorb the intense heat generated by friction with the air molecules. The challenges of achieving human spaceflight were immense, encompassing not only the technological hurdles, but also the human element. The selection and training of cosmonauts represented a critical step. The selection process was rigorous, focusing on physical fitness, psychological resilience, and technical aptitude. Candidates were subjected to extensive medical evaluations, simulated flight conditions, and intensive training programs. Yuri Gagarin, the first human in space, epitomized the qualities that Korolev sought. Gagarin's selection was a testament to his character, his piloting skills, and his ability to withstand the extreme stresses of spaceflight. His calm demeanor and unwavering dedication made him an ideal choice for this historic mission. The development of the necessary safety and control systems was equally crucial. The Vostok spacecraft incorporated a sophisticated guidance system to navigate in space and a system to ensure a safe re-entry trajectory. Redundancy was built into every system to minimize the risk of failure. These systems were meticulously tested and refined to ensure the cosmonauts' survival. The Vostok program's success was a watershed moment, a triumph of engineering and human endeavor. It catapulted the Soviet Union to the forefront of the space race and captured the world's imagination. The flight of Gagarin was a testament to Korolev's vision, his leadership, and the collective efforts of the many individuals who contributed to the program. It was a victory that resonated far beyond the confines of Soviet borders. The subsequent development of the Soyuz program demonstrated Korolev's continuing commitment to space exploration. The Soyuz spacecraft, designed to carry multiple cosmonauts and to conduct more complex missions, represented a significant advancement over the Vostok. While the specifics of the Soyuz's design fall outside the scope of this discussion, it is important to recognize that the program built on the lessons learned from the Vostok program. It incorporated advancements in technology and design, reflecting Korolev's continuous pursuit of innovation. The American space program, particularly Project Mercury, exerted an undeniable influence on the Soviet space program. While the two programs pursued different objectives and employed distinct technological approaches, there was a constant awareness of the other's progress. Korolev was keenly interested in the developments in the United States and used this information to inform his strategic planning. The competition between the two superpowers fueled innovation and accelerated the pace of space exploration. Korolev's role in the race to put a human in space was pivotal. He was the driving force behind the Vostok program, providing the technical expertise, the organizational leadership, and the unwavering determination to make it a reality. He championed the idea of manned spaceflight, overcoming bureaucratic hurdles and securing the necessary resources. His vision and leadership were the decisive factors in achieving this historic milestone. The Gagarin flight had a profound impact on Soviet prestige and global perceptions. It demonstrated the Soviet Union's technological prowess and its ability to achieve seemingly impossible feats. It inspired a sense of national pride and fueled a Cold War competition between the two superpowers. The flight of Gagarin was a triumph of human ingenuity and a testament to the power of scientific and technological innovation. It secured Korolev's place in history as a visionary leader and a pioneer of the space age. He built a program that changed the world. The echoes of Sergei Korolev's ambition resonate across the decades, a testament to the enduring impact of his vision. The Vostok program, a dazzling achievement, became a cornerstone for future endeavors. His leadership and technical brilliance, combined with the collective efforts of engineers and scientists, not only placed Yuri Gagarin in orbit, but also laid the groundwork for a sustained presence beyond Earth. The success of Vostok served as a powerful catalyst, propelling the Soviet space program towards more ambitious goals. The immediate aftermath of Gagarin's flight witnessed a surge in momentum. Korolev, emboldened by the triumph, immediately began pushing for subsequent milestones. The rapid succession of Vostok missions, each building upon the previous one, demonstrated a commitment to continuous improvement in the relentless pursuit of new frontiers. The development of the Vostok program, a direct descendant of Vostok, showcased Korolev's ability to adapt and innovate. Vostok, designed to carry multiple cosmonauts and to conduct spacewalks, represented a significant leap forward in space technology. This program, though shorter-lived than Vostok, offered crucial experience in extravehicular activity, a capability that would prove essential for future orbital operations. The political landscape of the Cold War, however, presented a complex set of challenges. The intense secrecy surrounding the Soviet space program, while offering some operational advantages, also had significant drawbacks. The lack of open communication and collaboration stifled the free exchange of ideas, hindering the rapid dissemination of knowledge and potentially slowing down the pace of innovation. The imperative of national security, paramount during the Cold War, took precedence over open scientific discourse. This environment, while understandable within the context of the time, ultimately limited the program's potential for international partnerships and the benefits that could arise from a wider pool of expertise. Despite these constraints, Korolev's influence extended far beyond the initial triumphs of the early space age. His focus shifted towards the creation of a space station, a long-term objective that would require complex engineering and logistical planning. The Salyut program, the first generation of Soviet space stations, was a direct result of his strategic foresight. These orbital outposts, designed to accommodate cosmonauts for extended periods, marked a transition from brief forays into space to sustained human presence. The Salyut program provided the platform for scientific research, technological experimentation, and the development of skills necessary for long-duration spaceflight. Parallel to the development of manned programs, Korolev championed the exploration of the solar system through robotic probes. The lunar program, designed to reach the moon, and the Venera program, aimed at Venus, showcased his commitment to scientific discovery. Though facing considerable technical challenges, these missions yielded invaluable data about the moon and the inner planets. The images and scientific measurements obtained from these robotic explorers dramatically expanded humanity's understanding of the solar system, contributing to the evolution of planetary science as a discipline. The impact of Korolev's work on contemporary science remains profound. His focus on modular design and standardized systems, for example, influenced the development of modern spacecraft and space stations. The techniques and technologies pioneered by his team, including life support systems, guidance and control mechanisms, and propulsion systems, continue to inform the design of contemporary space vehicles. The scientific data collected by the Soviet space program, including the information gathered by the lunar and Venera probes, provided crucial insights that advanced our understanding of planetary geology, atmospheric science, and the potential for life beyond Earth. The legacy of the space race itself is a complex one, marked by both intense competition and unexpected collaboration. While the rivalry between the United States and the Soviet Union fueled rapid technological advancements, it also created a climate of mistrust and suspicion. The race to reach the moon, for example, consumed vast resources and spurred innovation in various fields from material science to computer technology. The competition, however, gradually gave way to cooperation. After the Cold War, the International Space Station became a symbol of collaboration and shared scientific goals. The experience of the space race, with its triumphs and its failures, serves as a valuable lesson in the potential and the perils of international competition. Korolev's contributions extended beyond the realm of rocketry and space exploration. His leadership style, characterized by a blend of technical expertise, organizational skills, and unwavering determination, set a standard for project management in the space age. His ability to motivate and coordinate a diverse team of engineers, scientists, and technicians was instrumental in achieving unprecedented feats. The emphasis on teamwork, the meticulous attention to detail, and the relentless pursuit of excellence became hallmarks of the Soviet space program. These principles continue to inform project management practices in various fields, from engineering and technology to scientific research and industrial development. Examining the trajectory of Sergei Korolev's life reveals a narrative of unwavering dedication. He faced imprisonment, political persecution, and the constant pressure of the Cold War. Yet, he persevered, driven by an unyielding belief in the power of human ingenuity and the transformative potential of space exploration. His vision, his leadership, and his technical expertise were essential to the success of the Soviet space program. His contributions, far from being limited to the initial triumphs of the space age, continue to resonate in contemporary science and technology. The lasting significance of Korolev's work lies in his capacity to inspire. He demonstrated that seemingly impossible goals could be achieved through dedication, innovation, and collaboration. His legacy, therefore, is not merely a matter of rockets and satellites, but also the human spirit. He showed us that we are capable of pushing the boundaries of knowledge and reaching for the stars. In the annals of scientific and technological history, Sergei Korolev stands as a towering figure, a pioneer whose vision continues to shape our understanding of the universe and our place within it. His life and work serve as a powerful reminder of the enduring human quest for exploration, discovery, and the relentless pursuit of the unknown. His impact on the field of space exploration and engineering as a whole remains unparalleled.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.